So thanks very much for the invitation. Um, as I thought about what might be appropriate to talk today, there are a lot of regions of overlap between what goes on here and what goes on in EEB. I mean, beyond Jessica. Uh, there's work on infectious diseases that I could talk about, and I'll say a little bit about that, and sustainability on migration and on demography, among others. And I chose to talk about demography because it seems to me that the elements of mathematical demography are central to research in both OPR and EB. In fact, I knew about OPR before I ever came to Princeton, which was 33 years ago, and about the work of Ainsley Cole and others, and where demography and mathematical approaches to it have played a central role for decades. Indeed, demography is where I start my undergraduate course in theoretical ecology with this Leslie matrix projecting the population structure forward in time, also adding nonlinearity and other factors. But sticking with the classical view, I start pretty much with the beautiful key result. The stability of the age distribution goes back at least to Alfred Lotka, and the mathematical structure of Perron-Frobenius theory, et cetera. And it's a great start for my course. But knowing the consequences of a fixed age structure just raises a bunch of other questions. Like, what are the consequences of a changing life table? What causes those changes? Environmental factors, a government like China changing their one-child policy, et cetera. And after those changes, the population will move under the usual assumptions of a constant life table, et cetera, to a new stable age distribution. But there's an intermediate period. There's a transitional period. And I really enjoyed some years ago working with Tom Espenshade on this paper, looking at those transitional periods and the what is called in the literature momentum, and trying to characterize that. But the points of overlap go well beyond. They include the things I'm going to emphasize today: the evolution of life history phenomena, what's called dynasty theory. If you don't know what it is, I'll come back to that in a second. The allocation of resources during one's lifetime, for example, in biology to growth and reproduction, or in the economic example to consumption and savings. In fact, Jessica's written this paper a few years ago telling us why evolutionary biologists really need to become demographers, why there's this critical interface between them. So I'm going to start with a very simple model that was developed by a close friend and colleague of mine, Danny Cohen, who is an Israeli botanist. He's now in his 90s, so I don't think he's active anymore. But he was not a mathematician, but he had tremendous mathematical insight. And he wrote a paper more than a half a century ago raising this very simple question. An annual plant only does two things: it grows and it reproduces. It also disperses its seeds. But the critical question he asked is, when should this plant switch from growth to reproduction? It shouldn't start reproducing too soon, because if it does that, it can't produce anything. It shouldn't wait too long, because then there's not much of the season left. So is it a sudden change? Is it a gradual change? Delaying reproduction leads to higher productivity per unit time once you get there, but you got less time to use it, a shorter period to reproduce. There's also more competition, but that doesn't occur in Danny's model because his is an optimization model rather than a game theoretic model. So the question he addressed is, when should the plant switch to reproduction? And he showed that as long as you knew what the end of the season was, there was an optimal switch point. It's called bang bang in control theory, and that was determined by the environmental parameters. You grow for a while, and then you suddenly switch over entirely into reproduction. Danny had a student named Shmuel Amir, who then wrote a paper following up in which he said, well, what if the end of the season is uncertain? And he showed that in that case, it wasn't bang bang. There was gradual switching, graded switching. Reproduction was pushed even earlier, which meant less. When you have the earlier, you're making less investment per capita. And there are natural extensions, which not yet in the literature, on taking game theoretic approaches to this problem. I'm going to give you one or two other examples from biology that look very different, but I think are really the same sort of issue. My colleagues, I used to be at Cornell, my colleagues at Cornell, Steve Elner, who actually was my previous graduate student, and Nelson Harston, addressed the problem of diapausing eggs in zooplankton. These eggs are dropped into the banquet. They're essentially dormant eggs, and then they reappear at some point. You don't know what the end of the season is. The end of the season, in this case, is determined by when the predators come along and consume you. So they used this theory to calculate what the optimal switch point is when you should be dropping your eggs into the seed bank. And these evolutionary challenges generally go beyond optimization to game theoretic situations. An example, birds fly south for the winter and then come back to the north. When should they do that? What is the trade-offs of doing that? Well, if you come back too early, you're going to get hit by bad weather and wiped out. If you come back too late, all the good spots are taken. So it's a game theoretic problem. And working with my former postdoc, Yo Iwasa, tell you how long ago this goes back. Yo is now retired as a professor in Japan. We wrote a paper on the timing of life history events, and we looked at that problem. But there are a lot of other problems, for example, when plants germinate, et cetera, which are of the same type. You do one thing for a while, and then you switch over to the other thing. And what determines when you do that? And we're revisiting this issue now. There are a whole broad range of questions. Naomi Leonard has a wonderful postdoc named Mallory Gaspard. And Mallory and I and Naomi and Carla Staver are working on a lot of questions about plant allocation strategies. We don't have anything yet to report to you. But these are essentially problems that mathematics and what are called the calculus of variations. Actually, when Yo and I wrote the paper, we didn't do that, but I presented the work at a meeting a long time ago. And there was a great mathematician, applied mathematician in the audience, Joe Keller. He was one of the greatest applied mathematicians of the last century. And he came up to me afterwards and asked me to come to the blackboard with him. And he said, I think we could look at this as a problem in the calculus of variation, which it clearly was. And he mapped out the whole thing. And my hope was we were going to write a paper together, but then Joe passed away. But, and I could hardly read the notes he had given me. So Mallory took them and wrote them up. So now we've got a basis of doing something. We probably won't go back and look at the original problem, but there are a lot of problems we will look at in this way. And finally, there's a natural parallel in disease dynamics, which you all know about, but you probably wouldn't think about in this context. And we learned during COVID that there was a substantial undocumented coronavirus infections, people who didn't look like they were infected, but they were asymptomatically infected. Well, it turns out that just before COVID, my student, Shadi Saad Roy, who's at the top here, who was also jointly advised by Brian Grenfell and Ned Wingreen, but we were at a meeting and there was a session on the evolution of asymptomatic stages. Not that there were a lot of cases of it, but we thought, wouldn't that be a good idea for a virus to do? And why? It's a very similar sort of problem, which is, why do you stay asymptomatic? Well, it's just like the plant growing up. You build up a titer within the host, staying undetected until you decide now's the time to strike. I've got a big enough population. So what determines when you should switch or whether there should be an asymptomatic stage at all? So we wrote a paper in PNAS trying to look at the emergence of those stages. We used an epidemiological model, this one here. This is a standard epidemiological model with some modification. The usual epidemiological model goes from susceptibles to infectives to recovered. Sometimes you see something called an E class, which would be individuals often thought of as infected but not infectious, but it also could be infected and not showing symptoms, but infectious. So that generalizes this model. And then we wrote the equations down. Susceptible, infected, in stage 1, infected in stage 2, recovered. Standard dynamics, we could work those out. And then we said, but what if there's a second type that comes along, which has different rates? In other words, more likely to go into the asymptomatic stage first. When would an asymptomatic stage invade, and how long should you stay in the asymptomatic stage? What should determine the switching point? So we put the types in competition, and we showed, not surprisingly, because you have data, you know this can happen, that an asymptomatic infectious stage can emerge, but depending on the trade-off between transmission and progression. Intuitively, that's probably clear. So essentially delaying detection until an adequate titer built up. So let me go back to the Danny Cohn's paper now, because his simple model extends, I think, to a wide range of problems in life history theory. The problem of intergenerational transfer of resources is a central problem in evolutionary theory, as well as in microeconomics. The allocation of reproductive effort during your lifetime, the size of the litter, how big a litter, the trade-off between growth and reproduction. That's my son-in-law and my grandson. My grandson, however, has now graduated college, so it's a somewhat old picture. Think about the timing of reproductive events means you're looking at the trade-offs between L of X, the probability of surviving to age X, and M of X, the expected number of offspring at age X. This is a one-sex model. And these trade off against each other because you're making investments. Euler's equation defines the growth rate of the population, 1 equal to summation Lx mx e to the minus lambda x. But even if you were trying to maximize, which is what you might do in the expanding population, the growth rate, you still have a choice to make between Lx and mx. And if there's frequency dependence going on, that is, you're being affected by what other individuals are doing, becomes a more complicated problem. So let me then turn as a first application to the problem of litter size or clutch size. How many eggs do you have? And, if you make these calculations, and for example, for dogs, you may find that the answer is 3.7 or something of that sort. And in fact, that's probably realized by having 3 normal offspring and producing a runt that will survive during good times. But anyway, you have a decision. Do I make a few large eggs in which I make a big investment, or a lot of small ones, like a plant dispersing thousands, tens of thousands of seeds and just hope some of them take? So what's the trade-off between them? So the classical theory goes back to David Lack, a great ornithologist and biologist. He said, well, what you really care about is how many offspring you have at the end of the year. So I should maximize the number of offspring I produce times the probability of survival. That seemed rather intuitive, and that sort of stuck in the literature for a while. But there's a problem with that. This was pointed out to me by my former student, Adi Livnat, who said, and this was part of his thesis, well, it's true, you have the same number of offspring at the end of the year, but suppose I produce a few offspring that are rather strong and make it to the end. You produce a lot that make it. Mine are stronger than yours, and that should be carrying over into future generations. So this complicates Lack's picture. So together with Steve Picalo, we wrote a paper in which we looked at this trade-off. We said we have 2 kinds of individuals, what we called it's a transgenerational model, and we looked at mutation and recombination in particular and what their effects on it, and I'll come back to that. And the uncertainty in the process, the more uncertainty we showed, the more it's selected for large clutch sizes in which you make small investment. The nature of the model was we broke the population up into what we called idealists, which are individuals that produce a small number of clutches and make a big investment in them and in the future, and hedonists. Maybe you don't like this terminology, but it worked. And these are ones that produce large clutches, investing not too much in each one of them. So what's the trade-off between them? Well, we built this model in which we looked at hedonists and idealists and their success in future generations, but we also allowed for mutation, which would take a hedonist and turn it into an idealist in the next generation. Of course, that was complicated because when it if an idealist decided to switch to be a hedonist, it was doing so, at least for the first generation, with this extra resources that had accumulated up till now, and vice versa. And therefore, it's really a four-dimensional model we had to look at. And I won't show you the graphs of this. I had them in there, but took them out. But one can modify the mutation rate or the recombination rate. And the key thing is mutation. What's the effect of mutation and recombination? Well, if there's a lot of mutation and recombination going on, this reduces my relatedness to my children, to future generations. This, we showed, selects for forgetting about the future and buying more lottery tickets and making small investment in them. In general, what this shows is uncertainty can increase or decrease current consumption. For example, constantly as I get older doing different kinds of wealth planning, if you're worried about your future resources in a rather stable world, you're going to set some aside for savings to make sure the money's there. But if you knew the world was going to end tomorrow, or at least you knew your world was going to end tomorrow, if that might lead to a greater spending now. My lawyer, and when we were doing our estate planning, said, spend it down, which I didn't take as encouraging, actually. And in finance, uncertainty about what people will do may lead to uncertainty about fiscal policy. So in economics, Gary Becker won the Nobel Prize for his work on what's called dynasty theory. And dynasty theory was basically the theory of how much you leave to future generations, optimizing your consumption, et cetera. And your children are extensions of you. So it's as if you lived forever. I regularly attended a meeting. We met at least once a year with leading economists. And one of them, to whom I was closest, was Kenneth Arrow, who was one of the great economists, one of the greatest economists for sure, of the last 100 years. And I said, you know, in dynasty theory, your children are sort of an extension of you. It's as if you lived forever. It's like assuming you have one child. But in biology, like in the work that I just described with Adi Livnat, you may have lots of children or you may have none. There's variation. Does that matter for dynasty theory? And he thought about it for about 30 seconds and he said, no. But to tell you something about Ken, we met regularly, and 4 years later, he came up to me and he said, you know, you asked me a question 4 years ago and I gave you the answer. I've been thinking about it. I gave you the wrong answer. So we started working on this and we wrote a paper called Intergenerational Resource Transfers with Random Offspring Numbers, trying to compute what the optimal strategy would be under various conditions for how much you should consume versus how much you should leave for your offspring. This appeared in PNAS in 2009. And what we assumed is that every individual has K units of wealth. One should, of course, there are lots of directions one could modify from this by allowing individuals to have different amounts of wealth, and you'll see why that's important in a minute. Each individual has K units of wealth to divide between current consumption and reproductive investment. We defined a function U of C, which is the utility of consumption, and we took it to be a power law. which was a standard sort of thing, a power law that sloped up but leveled, it didn't level off, but slowed down in its growth. There's a parameter beta in here, which describes your discount rate, how much you care about your offspring in relationship to how much you care about yourself. So obviously that's important in the optimization. And that may be subject to selection as well. N is the number of offspring you have, but that's drawn from a distribution. Now, not everybody has the same number. And then the amount that you have grows because you invested in the markets. This is the growth rate of the resource, whatever you're transferring or per generation. So there are two kinds of discount rates in this. It's the discounting the future and the discounting of your interest in your offspring. And then the control variable in this is how much you consume currently. So we use the dynamic programming approach, computing the total welfare along the optimal path. And the total welfare is the utility of consumption at a particular time, plus the utility, the total welfare of your offspring, multiplied by the number of offspring you have, multiplied by beta, how much you care about them. So what's in the bracket there is the function you're really trying to maximize. So the idea is to maximize this, but it depends upon future generations. So you have to solve it as a dynamic programming problem. So as I said, we assume U to C to be concave. It's this power law function. And we showed that you could solve this dynamic problem by making an ansatz, that is a prior assumption, about what the solution is and showing that it really was the solution to the problem. And in this, just like the examples I've shown you before, the effect of uncertainty is similar to what it was in the evolutionary examples. Uncertainty can either increase or decrease your current consumption depending on the curvature of the utility function. So it might lead to consuming more now or less, depending on what the nature of the uncertainty is. So it can lead to more savings or to more consumption, depending on the source and the nature of the uncertainty. Well, we set out to find out what the optimal strategy is, but then what Ken as an economist, got very excited about, he says, this tells us how we can project forward what the wealth distribution is going to be in the population. Because we know if everybody's doing the optimal thing and we start with a particular wealth distribution, that's going to change over time, depending on what people leave to their offspring. And we showed that, in fact, it led to a log normal distribution with a variance that was increasing over time. In other words, the inequality, the inequity in the population was increasing over time at a rate that was proportional to the degree of uncertainty, the degree of variance in the number of offspring. So this was a good start, but it's not what the data show. The data are more like this. They look like a power law. This is a wealth distribution, and I'll show you a couple of these slides. This is the wealth distribution, and it looks like a power law. I'm sorry, like a normal distribution, sort of. This is actually, this is not on a log scale, but the tail, as you see, is very fat on the right. It's asymmetric. It's what's called a Pareto distribution or a power law tail. So why should that be the case? Here's some other evidence of of what the distribution looks like with the longer tail on the right. And Victor Yakovenko, who's at the University of Maryland, and others have been looking at these, and I'll come back to him at the end, looking to quantify these power law distributions. This is for wealth, but also income they're looking at least in the UK and the US. And there are various extensions that we looked at. Some of them we looked at in the paper. First of all, in the original model, we said you make a decision once in your lifetime, but what if you keep adjusting your decisions as you get information about how many kids you have and how many kids you're going to have? You can make those calculations. Obviously, it becomes mathematically harder. But the thing we were most interested in, which we did not put in the paper, is why were we getting the wrong tail on it. How could we modify the tail? One idea, which we rejected, which means Ken rejected, is maybe richer people have fewer offspring, and therefore they're leaving each one of them a larger share, and that could make those at that tail richer. He thought there was very little data to support that hypothesis. Maybe you don't, there are examples of this, you don't treat all of your offspring the same. That is, maybe in some cultures, the oldest will be given a larger share, and that could modify it. But the thing that, and there are other sorts of uncertainty, but the thing that we most thought would be the explanation is, Princeton is getting a huge return on its investment, better than you or I could get, I assume. Rich people have ways to get higher returns on their investment than poor people. They get better advice, they pay for it, and invest in things in different ways. And that obviously has the potential to make the rich end of the spectrum even richer. And the data show that and I think the increasing, and I Ken argued this too, inequality in our society is not only one of the great driving forces for the polarization and problems we're having, but also, he said, is still an economic mystery. My current graduate student, Matt Chung, I had a previous graduate student, I'll mention her work in a second, Sarah Drohan, who worked on this. Sarah had the good fortune to be able to go out and visit Ken for an extended period while he was still alive, and produce a PhD thesis. Matthew has picked up this problem, and this is a paper which we have in review. Actually, it's a revised version we've sent back to PNAS, which tries to modify this by trying to do it analytically. What Sarah did was to show numerically that the fact that rich get higher returns, the wealthy gets higher returns, will tend to broaden out the tail. But analytically, there are problems with it, and I'll tell you why. So this is our paper, and going back to the Piketty and other economists who observed the Pareto distribution. Just repeating what I just said, the return rate is greater for wealthy individuals. And Sarah showed numerically that this worked. But the problem is that the way we solved the dynamic programming problem by assuming a solution and showing it was the solution didn't work. That was complicated in this scheme, and we haven't been able to come up with an ansatz. But if the power law in which we use for consumption, which is consumption to the 1 minus alpha over 1 minus alpha, in the limit, as alpha tends to 1, tends to a logarithmic curve. So actually, you have to add a constant to even get L'Hopital's rule to work there, but it's adding a constant to the utility function doesn't change anything. So we looked at the limiting case, or Matthew looked at the limiting case really, as alpha tends to 1, which gives you a logarithmic instead of an isoelastic elasticity. And he was able to come up with an ansatz to show formally that, in fact, you got power law tails. We're not finished with it because you lose some of the features that were that exist with the power law function. But if you perturb off alpha equal to 1, I think you can show that everything now holds. So the skewed distribution further to the right, if you start with a power law distribution, you keep a power law distribution. But it's still a problem, and it's not clear what to do in our societies about reducing the inequities. So what are some of the other considerations that we haven't taken into account, but I hope to? One is, this is all an optimization of a sort. I mean, there's you and there's your children. Remember, in the previous model, we looked at mutations and things. In general, whether you have a mutation that reduces relatedness, or you just have pro-sociality in which you care about the excuse me, the children of others. This can complicate the picture. This can lead to more altruistic behavior, less present consumption. And then there are market interactions as well, because this is not just a life history determination, it's how does the market affect these things? And Yakovenko and his colleagues have been looking at these universal patterns of inequality, and they take a very much a market-based approach. This is a final thing I want to tell you about. I've been working for years with Avinash Dixit, professor emeritus in economics here, on the effects of pro-sociality. And we wrote a paper together with my former student, Andrew Tillman, which said, what if we have a population that's broken up into subgroups? And for the purposes of this paper, those groups are non-overlapping, but in work we're doing now, we're trying to let them overlap as well. And because that turns out that leads to more cooperative behavior. So the idea is that individuals have to make a decision. They have resources that they can either retain for themselves or they can contribute to the public good. If they contribute to the public good, it's mostly redistributed to others in their group, but there's some leakage to other groups. So if it's clean air you're preserving, then there's leakage to the next town over. And you have some pro-sociality. In other words, you care, and I'll show you the formula, I think. You care about other individuals in your group. And the question is, can this lead to pro-social, to cooperative behavior? So just summarizing what I just said, we present this is from the paper, we present a general theoretical model where society is split into subgroups. People care more about the welfare of others in their own subgroup than they do in the outgroups. But the individual contributions to the public good may spill over to some extent and benefit individuals in other groups. And then the question we asked is, to what extent pro-sociality closes the welfare gap between the Nash equilibrium you would get without pro-sociality and the social optimum. So whenever you address a problem like this, you can look at what the social optimum would be, what the Nash equilibrium would be if everybody were selfish. You could ask for second best solutions, but now if we incorporate pro-sociality, and obviously if you make the pro-sociality high enough, you're going to get up to the social optimum. But what about in between? How does that depend? And so that's what we look at in this paper. And this is the nature of the model. Your individual utility is the payoff you get. So little x is what you keep for yourself. Little z is what you put into the public pool. Capital Z is the aggregated public good. And Z sub G is the aggregated public good in group G. So your payoff immediately is the first term, Y of your investment in yourself and the public and the local public good, which includes spillover from other terms, minus a cost function based on your total investment in these two things. And by the way, we also did, here there's a quadratic cost function, but we also did an analysis. If you have a fixed budget that you have to spend on these things, it doesn't change anything. And then your the function you're going to maximize also includes the immediate benefits others in your group are getting. Those are all subscripted by the group, multiplied times how much you care about them, the gamma of G. So just to summarize what's here, capital Z sub G is the public pool in group G. Gamma is the pro-sociality within the group. X and Z are the private and public efforts. And as I said, we also consider a fixed budget. And from this, we can calculate what the Nash equilibria are, et cetera. And we are looking at more complicated topologies. I said allowing groups to overlap, or you could simply have a relationship to every individual in the population. But the analysis obviously gets much harder. Well, a natural question that arises from this is, okay, if you have prosociality, um, that can help, but why do you have prosociality? So Avinash and I wrote another paper um, to show how prosociality can emerge endogenously. And it's a mathematical model, but basically the way it works is like this. You're better off in a pro-social world. I care about my children. I want my children to live in a pro-social world. So I will take steps now, like making investments in education to increase um, pro-social behavior. And we showed in that way that pro-sociality can evolve. Ours is not the first such model to do that. First one I know about, it's slightly different in nature, is due to Herb Gintis, who was an economist, passed away a few years ago, and a few others. Anyway, so let me turn to some concluding remarks. I work on ecosystems and I work on social systems. Ecosystems and the biosphere are what are called complex adaptive systems. If you're interested in the topic of complex adaptive systems, David Krakauer, who's the president of the Santa Fe Institute, is giving a lecture tomorrow, a public lecture in Makash 50 at 5 p.m., I think, talking about complex adaptive systems. What are they? They've gotten a lot of attention in many different, in social sciences and biological sciences and physics and in business. Um, they are they're systems made up of lots of individual agents, all pursuing their own selfish agendas. And they interact locally, and there are emergent properties that are based on those interactions. Not only the ecological systems, but so too are the socioeconomic systems with which they are interlinked. The fundamental macroscopic properties, for example, of the biosphere, emerge from lower level interactions. Things like the distribution of species abundances, energy flow, nutrient cycling, ecosystem services. These are all things that we derive from the systems at large, but are obviously determined by lower level processes. Just as emergence typifies problems in economics, the relationship between microeconomics and macroeconomics, ecological systems are the same. And in fact, it's not a big surprise to that because the ecological systems and economic systems are very similar. That's why they both start with the phrase eco, or the letters eco, meaning house. So all of this means that there are a number of mathematical challenges that have to be addressed. How do we relate phenomena across scales, develop an appropriate statistical mechanics from cells to organisms, to collectives, to societies, to, to the biosphere, etc. And to ask questions like how robust are the properties of systems? How does the robustness of those macroscopic properties relate to the microdynamics on finer scales? Might systems be suddenly changing? Might we lose the stability of the system? Are systems at critical points? And are there early warning indicators? All of these are extremely hot areas of research. And for me, the most difficult, the most challenging, and the one maybe with the most at the interface between what we do in EEB and what you do here is how do we manage the commons across scales and conflicts of interest? Indeed, ecology and economics are two sides of the same coin. Um, and we've been pursuing that. Ken and I and Paul Ehrlich wrote a paper a few years ago called Some Perspectives on Linked Ecosystems and Socioeconomic Systems. That was in a book in honor of Partha Dasgupta. And more recently with Tassos Zapapadeas, great environmental economist, we wrote a book called a paper in the annual reviews called On the Coevolution of Economic and Ecological Systems. For me, this is one of the most exciting areas. Not only what are the parallels between economic and ecological systems, but what are their interactions? What's the interplay between them? So in summary, the issues that I think you confront here in OPR bear a lot in common with the issues that we confront in EEB. No surprise in that you have cross-appointed people. Hence, it's also no surprise there's a lot of great potential for cross-fertilization. And I'm here because I'm hoping we can find a lot more areas for collaboration. Thanks very much.